Motion in our daily life can take many forms. The Diwali rocket executes translatory motion. Some more examples of translatory motion are the motion of a parachutist, a bullet fired into the air, and a football kicked into the air. The other type of motion we come across very frequently is rotatory motion. The rotating motion of the blades of a fan is an example of this type of motion. Other examples are the rotating motion of the blades of a mixer grinder and the rotation of the blades of a turbine. In these examples, the motion repeats itself after a certain fixed interval of time. Hence, this type of motion is called periodic motion. Periodic motion is exhibited by all the planets revolving around the Sun, since each planet has a fixed time interval for each revolution around the Sun. Periodic motion is also exhibited in other cases, such as the to and fro motion of a sewing machine needle and the movement of the piston of an engine. The to and fro motion of a body is called oscillatory motion. Let us consider a string fixed tightly between two walls. When the string is plucked and released, it executes to and fro motion. All oscillatory motions repeat themselves after regular intervals of time and hence are periodic motions. However, every periodic motion need not be an oscillatory motion. In the oscillatory motion of a body, there is a force that always directs the body towards the position, which is the position of zero displacement. This position is referred to the mean or rest position. This force is the restoring force. For example, in the spring shown here, which is fixed to a rigid support and the mass attached to the spring oscillates. The spring oscillates about the mean position. The motion of the bob of a simple pendulum is another example of oscillatory motion. In the simplest form of oscillatory motion, the restoring force on the body is proportional to its magnitude of displacement, but is opposite in direction to the displacement from the mean position. This type of motion is called simple harmonic motion. Simple harmonic motion is the to and fro motion of a body, where the force is always directed towards the mean position and is proportional to the displacement but in the opposite direction. Thus, the simple pendulum and the spring with vertical oscillations are executing simple harmonic oscillations. The oscillation of a boy on a swing is an example of simple harmonic motion. In practice, oscillating bodies come to rest at their rest position due to external forces which oppose the motion, called damping forces. The energy of the oscillating bodies dissipates due to the damping forces, and hence the oscillating bodies lose energy in the course of time. Hence, the boy swinging on the swing gradually comes to rest. To maintain the oscillations, the swing must be pushed by somebody such that the swing always reaches the same extreme positions. The person pushing the swing applies an external periodic force, which allows the swing to continue its oscillations in spite of the damping forces. Thus, understanding the concept of oscillatory motion helps to understand various physical phenomena. As we learned earlier, all oscillatory motions, like that exhibited by a pendulum, are periodic motions. The smallest regular fixed interval of time, after which the motion of a body in oscillatory motion repeats itself, is called the periodic time or time period, denoted by t. Time period t is measured in seconds. Consider the example of a simple pendulum that exhibits periodic motion. Now, allow the pendulum to oscillate freely and note the time taken, say, for 10 oscillations. Here, time period t will be equal to the total time taken for the given number of oscillations divided by the number of oscillations. If the pendulum takes 20 seconds for 10 oscillations, the time period of the simple pendulum will be equal to 20 divided by 10, which is equal to 2 seconds. Therefore, the time period of this simple pendulum is 2 seconds. What is the frequency of an oscillatory motion? The frequency of an oscillatory motion is the number of oscillations performed in a unit time, that is, 1 second. It is denoted by the letter n. In this case, the pendulum shown executes 10 oscillations in 20 seconds. That is, in 2 seconds, it executes 1 oscillation. Here, frequency n will be equal to the number of oscillations by the time taken, which on substitution gives the value 0.5. Therefore, frequency n is equal to the reciprocal of time period t. Frequency is measured in cycles per second, CPS, or Hertz, and is denoted by the letters Hz. Named after the scientist Heinrich Rudolf Hertz. Now let us discuss the displacement of a body executing oscillatory motion. Consider the same example of the pendulum moving. When the pendulum moves away from the mean position O towards the extreme position, its displacement from the mean position increases. And when the pendulum returns towards O, the displacement from the mean position decreases. In oscillatory motion, all displacements are measured from the mean position. The displacement can be positive or negative after fixing the reference position. For example, if the same pendulum were to oscillate towards the left of the mean position O, its displacement can be taken as negative, considering the right side of the reference position as positive. The displacement variable in general can be understood as the variations in physical quantity with time in a broader sense when the variable involved oscillates. The varying electric current in an AC circuit and varying electric and magnetic fields in an electromagnetic wave can be considered as displacement variables. Since the displacement in periodic motion varies periodically with time, the displacement theta can be expressed as a periodic function of time, like f of t is equal to a cos omega t, where omega is the angular frequency measured in radians per second. The condition for the function f of t to be periodic is that if the argument of the function, which is omega t, is increased by integral multiples of 2 pi radians, the value of the function remains the same. Thus, a cos omega t plus 2n pi must be equal to a cos omega t, where n is any integer. In other words, the function is periodic with the time period t, when f of t plus t is equal to f of t, where the time period t is equal to 2 pi by omega. The function f of t is equal to a sine omega t is also a periodic function, which implies that a sine omega t plus 2n pi is equal to a sine omega t. A linear combination of two periodic functions is also periodic. For example, a periodic function can also be of the form of f of t is equal to a sine omega t plus b cos omega t, with a and b are constants. If the constant a is equal to d cos phi and the constant b is equal to d sine phi, where d and phi again are constants, then we can rewrite the function as f of t is equal to d cos phi sine omega t plus d sine phi cos omega t. Simplifying the expression using trigonometry, we get f of t is equal to d sine omega t plus phi. We are aware of the constants a and b. Hence, we need to express the new assumed constants d and phi in terms of the known constants a and b. Using trigonometry again, we get the constant d is equal to under root of a square plus b square, and the constant phi is equal to tan inverse b by a. We discussed a periodic function that is a combination of a sine and a cosine function. The importance of these two harmonic functions is due to the mathematical result proved by French mathematician Jean-Baptiste Joseph Fourier. According to the result proved, any periodic function can be expressed as a superposition of sine and cosine functions with suitable coefficients. Consider a body attached to a spring. When the spring is compressed and released, the body attached to it oscillates back and forth between the two extreme points, marked as plus A and minus A. As the body moves away from its mean position, it experiences a restoring force, which attempts to bring it back to the mean position. This to and fro motion being executed by the body is called simple harmonic motion. The displacement of the particle from the origin is a function of time t. The displacement x of a particle in simple harmonic motion can be expressed as x of t is equal to a cos omega t plus phi. Let this be equation 1. In simple harmonic motion, the variation of the displacement of a particle with time t can be denoted by the displacement versus time graph. A periodic motion where the displacement of an oscillating particle varies sinusoidally with time t can be called simple harmonic motion. Since the displacement x of the particle is dependent on the cosine function as given by equation 1, the displacement will vary from plus a to minus a. In the argument omega t plus phi, consider the value of phi is equal to 0. If time period of the particle in simple harmonic motion is t, then At time t is equal to 0, the particle will be at the extreme position. Since x is expressed by equation 1, will be equal to plus a. When time t is equal to t by 4, the particle will be at mean position. For the oscillating particle, when t is equal to t by 2, it is at the left extreme, and when it is at t is equal to 3t by 4, it is again at the mean position. When t is equal to t, it returns to the right extreme position plus a. Now let's discuss the amplitude of the motion. The maximum displacement of a particle from the mean position executing simple harmonic motion is called its amplitude A. In simple harmonic motion, the quantity omega t plus phi, which varies with time, is called the phase of the motion of the particle executing simple harmonic motion. At time t is equal to 0, the phase is equal to phi, and this is called the phase constant or the phase angle. It is the initial phase of the particle executing simple harmonic motion. In simple harmonic motion, amplitude is the only quantity that is time independent, whereas displacement, velocity, acceleration and the phase angle omega t plus phi are time dependent. As shown in the graph, two simple harmonic motions may differ in the phase constant phi in spite of having the same omega values. For simplicity, if phase constant phi is considered as 0, equation 1 above can be written as x is equal to a cos omega t. We saw that when time t becomes equal to the time period t, the displacement x becomes equal to a. This implies that cos omega t is equal to 1 or omega t is equal to 2 pi. Then, omega is equal to 2 pi by t. This omega is called the angular frequency of the simple harmonic motion, and its SI unit is radian per second. Consider a particle P revolving along the circle of radius a with the center of the circle at the origin O of the coordinate axes. This particle is called the reference particle. Let the particle revolve with the time period t and a constant angular velocity omega. This circle is called the reference circle. Since angular velocity is constant, we can say that the particle executes uniform circular motion. After the particle has moved for some time in the reference circle, take a projection of the particle on the y-axis. Label it as P'. As particle P revolves along the circular path, its projection moves up and down along the y-axis, with the mean position as O, and the extreme ends of this diameter of the reference circle along the y-axis as the extreme positions. Now, consider the position of particle P at time t equal to 0 on the x-axis. At the end of t seconds, its position changes. The angular displacement of the particle at the end of t seconds is omega t. At any time, OP denotes the position vector of the particle P. Consider the position of the projection of the particle along the y-axis when the particle moves through an angle omega t in a time interval t. The projection of the particle moves from the origin to the position as shown in the time t seconds. The displacement of the projection of the particle y is then obtained using trigonometric ratios of the right-angle triangle thus formed. Sine of the angle omega t is the ratio of opposite sides, which is the displacement of the projection of particle p dash, that is, OP dash, represented as y, to the position vector of the particle OP, whose magnitude is equivalent to the radius a of the reference circle. Thus, we get y is equal to a sine omega t. The motion of the projection is oscillatory, and its displacement varies sinusoidally with time. Thus, the motion of P dash is simple harmonic motion. If the reference particle P executes uniform circular motion, its projection executes simple harmonic motion along the diameter of the reference circle. Here, A is the amplitude of the point P dash executing simple harmonic motion. In another case, consider the position of the particle P at time t equal to 0, such that OP makes an angle phi with the x-axis. It then executes uniform circular motion with angular velocity omega along the circumference of the reference circle. At the end of t seconds, the position of the particle is such that OP makes an angle omega t plus phi with the x-axis. Then, the displacement of the projection of P executing simple harmonic motion along the diameter of the y-axis can be written as y is equal to a sine omega t plus phi, where a denotes the amplitude of simple harmonic motion, which is the radius of the reference circle. As with the projection of the reference particle on the y-axis, the point marked in green is the projection of the reference particle on the x-axis. As the particle revolves along the circular path, its projection moves to and fro along the x-axis, executing simple harmonic motion with mean position as O, and the extreme ends of this diameter along the x-axis as the extreme positions for simple harmonic motion. At time t is equal to 0, the revolving particle makes an angle phi with the x-axis. From this position, when it moves through an angle omega t in a time interval t, its projection moves from s to t along the x-axis. The displacement of the projection executing simple harmonic motion along the diameter along the x-axis can be written as x is equal to a cos omega t plus phi, where a denotes the amplitude of simple harmonic motion, which is the radius of the reference circle. If the revolving particle began its journey from the end of the diameter, then the projection on the diameters along the y-axis, its displacement will be 0, and the initial phase angle phi would be 0. Then, displacement y is equal to a sine omega t, which is equal to 0. As you know, when a reference particle revolves along the reference circle with a constant angular velocity, omega, the projection of the particle on the diameters along the x-axis and y-axis executes simple harmonic motion. The particle executes circular motion with a constant velocity v, whose magnitude is equal to a omega, where a is the radius of the reference circle. For simplicity, if we assume the initial phase phi is equal to 0, then the two components of velocity v are v cos theta and v sin theta respectively in the directions shown. Then, the component v sin theta represents the velocity of the projection, which is executing simple harmonic motion on the diameter along the x-axis. Velocity of a particle in simple harmonic motion is equal to minus v sin theta. The negative sign is due to the direction of the velocity at that instant, which is opposite to that of the positive x-axis. If the particle has an initial phase phi, the velocity of simple harmonic motion can be written as minus v sin omega t plus phi or minus a omega sin omega t plus phi. Now, let us discuss acceleration in simple harmonic motion. Acceleration of the revolving particle will be the centripetal acceleration AC, denoted by v square by a or a omega square. This centripetal acceleration has two components: AC cos theta along the x-axis and AC sin theta along the y-axis. If the initial phase phi is equal to 0, the acceleration of the projection, which is executing simple harmonic motion along the diameter along the x-axis, is equal to minus AC cos theta, since this component is directed opposite to the positive x-axis. If the initial phase phi is not equal to 0, the acceleration of the projection in simple harmonic motion is equal to minus AC cos omega t plus phi, which in turn can be written as minus a omega square cos omega t plus phi. On rearranging, we get minus omega square into a cos omega t plus phi. The quantity a cos omega t plus phi is the displacement x of the particle executing simple harmonic motion. Hence, the acceleration of the particle executing simple harmonic motion can be written in terms of its displacement as minus omega square x. Observe the graphs for the particle in simple harmonic motion. The first graph is displacement versus time for the particle in simple harmonic motion. The second graph is velocity versus time for the particle in simple harmonic motion. The third graph is for acceleration versus time for the particle in simple harmonic motion. From the graphs, we see that the phase difference between displacement and velocity is pi by 2 radian. The phase difference between displacement and acceleration is pi radian. Consider a body that executes simple harmonic motion. With amplitude A. In this case, the force F of t always acts towards the mean position of the body and is proportional to the displacement of the body. Hence, this force is called the restoring force in simple harmonic motion. For simplicity, if we assume the initial phase phi to be 0, then the displacement of the body is x of t is equal to a cos omega t. Earlier we saw that the acceleration of a particle in simple harmonic motion is equal to minus a omega square cos omega t, which is equal to minus omega square x, since the displacement in simple harmonic motion is equal to a cos omega t. Using the relation force F equal to mass into acceleration, we get the equation for the force on the body of mass m in simple harmonic action, as F of t is equal to minus ma omega square cos omega t, which is equal to minus m omega square x. Let this be equation 1. Earlier we had seen that the force due to simple harmonic motion can be written as F of t is equal to minus kx, where k is the force constant and x is the instantaneous displacement of the body. Let this be equation 2, equating 1 and 2 and simplifying. We get m omega square is equal to k, or omega square is equal to k by m. Hence, angular frequency omega is equal to the square root of k by m. Thus, if the force is directly proportional to displacement, it is called a linear harmonic oscillator. On the other hand, if the force depends on displacement but is not directly proportional to displacement, it is called a non-linear harmonic oscillator.